In this lesson, we shall focus on applied mathematics APM 3711. We are actually looking at numerical methods. To start with, we shall actually discuss a very important notion of what we call the Pade approximation, R4 of X. Find, for example, as part of what we need to do is to make sure that we cover enough ground based on the kinds of things that you're expected to know for assessment purposes. And the Pade approximation is examinable. And therefore, we will make significant effort to make sure that you understand the Pade approximation. So find the Pade approximation R4 of X with denominator of degree 2 to the function f of x equals 4 plus 4x squared minus 2x to the 6th power. Okay, right. So what do we do in this particular case, and how do we, for examination purposes, determine the Pade approximation of a given function? This is what we do. So we're going to deal with R4 of x. Right, so now the R4 of x can be seen as A naught plus A1x plus. So we're covering the concept of the Pade approximation. Right, and we have A2x squared. Right, the denominator must be of degree 2. And therefore, you'd have that. Always this is 1. This is always 1 plus B1 x plus B2x squared. Exactly like so. Now, the question then is, in other words, what is the degree of this rational function here? We then regard the degree of this rational function as being 4. That is why these are 4 of x. The denominator is of degree 2, so that is quadratic, and we make sure always that for the denominator to always be not 0, we put the number 1 there, and these variables will always be put there. Okay, so we continue to then make the following observation here. So if this becomes the Pade approximation, so we note therefore that the Pade approximation, so very key to this is writing the following so that you're able to follow even during your own leisure when you go through this discussion. We say the Pade approximation. Right, so the Pade approximation is, okay, we are here, never mind that. Okay, so the Pade approximation becomes exactly this one down here. What does this therefore give? So this gives, what does it give? It gives R4 of x minus f of x. What is therefore the R4 of x? R4 of x we've already seen here is A naught, A1x, A2x squared, all divided by 1 plus B1 x B2 of x squared. We subtract f of x, which is this, which is 4 plus 4x squared minus 2x to the 6th power, which will therefore give us minus 4 minus 4x squared plus 2x to the 6th power, which gives now the question is, what would this in the end therefore be able to afford us? Right, so this will afford us a product accordingly. Right, and therefore we need to multiply this. If we are to claim therefore that this is sort of the approximation of this. That will therefore mean a couple of things. But it will then mean that the difference of these two here should almost be 0. Now, if the difference of these two equals 0, what then are we able to obtain at the end of this? Right, so you can actually be in a position to write the following. You can be able to write, for example, R4, x minus f of x equals, LCD is there, A0, A1x, A2x squared. If need be, can put a minus like this, 4 plus 4x squared plus 2x to the 6th power, multiplied by the denominator, taking the LCD, which is 1 plus b1x, b2x squared, all over. All over the common denominator, 1 plus b1x, b2x squared. Just like so. And at this point, we consider this very seriously. But also, if this becomes the approximation of this, we are then able to make certain observations about what happens here as a consequence. It therefore means we can be allowed to then say this therefore becomes 0, which equals A0, A1x, A2x squared, 4 plus 4x squared, 6th power, b2x squared. Okay, so that is what we're able to get. So we actually have that 0 expression from the Pade approximation relation. We therefore proceed to then say at this point, we need to carry this forward. So we proceed to then say, we therefore have that 0 is A0, A1x, A2x squared, 4, 4x squared, 2x to the 6th power. See here. Right, so this is going to be negative. If you factor out this negative, this is going to be a negative. It's going to be taking the same sign there. It's going to actually be 4 plus 4x squared minus 2x to the 6th power. And it's going to be negative 2x to the 6th power, which is exactly what we have here. 1 plus b1x, b2, b2 x squared. Exactly like so. What is this? Okay, we perform the algebraic manipulations that are necessary. And we're able to then achieve that is 0, A1x, A2x squared. Distribution. So now you have minus 4b1x cubed Okay. So minus 2x to the 6th power. X to the 8th power. X to the 8th power. Okay, it's just distribution. We open up the brackets. We check again. We have the 4 that multiplies through. 4 times 1 is 4, obviously negative, with the negative outside. 4 with the B1 is minus 4B1x, minus 4B2x squared. Then we take the minus 4x squared, we distribute, which is minus 4x squared. Minus 4x squared by this, it's minus 4B1x cubed, minus 4B2x to the 4th power. Then we have the minus 2x to the 6th power, it comes out of this. But obviously, agree it's going to be actually exactly a plus. So because of the negative, so it's going to be plus there, and plus there. So you're going to be actually having the 2x to the 6th power, but it's going to be positive because it's negative. And then now also there's 2x to the 6th power with the b, which is 2b1 x to the 7th power. And then this one is going to be 2b2 x to the 8th power. Okay, we're good. It remains to just group like terms together. And if we do group the like terms together, we're able to actually obtain the following. What exactly are we able to obtain here as a matter of fact? Let us look at the constants. Right, so the constants become, right. So we continue. Okay, yeah, we continue, please. Now, when you continue, we make certain observations about what happens here as a matter of fact. What observations are we able to see? Right, we're able to see that. Okay, group like terms, please, all constants, it's going to be A naught. There's A naught, and then there's a minus 4. And there's no other constant term, so you're going to put A naught to minus 4. Right, so if that is the case, this is our A naught. And then we continue. Let us check. Then we have the linear terms. The x terms. There is an A1x. So there is A1x, and then there's 4b minus 4b1. Minus 4b1x. And then there is an x term. No other. And then we have x like this. Then now we'd have the quadratic terms. A2. Right after we have the A2, you would have the minus 4b2. Minus 4b2. Right, minus 4b2 for the x squared, minus 4. So A naught, this. A1, that, okay? And then A2 minus 4b2, the minus 4. So we're done with all those, and then now we're going to look at the cubic terms. And the cubic terms would be plus minus 4b1. Okay, yeah, it's only one cubic term. So you're going to put minus 4b1 x cubed. And then the x to the 4th power minus 4b2 x to the 4th power x to the sixth power. Right, so we're going to check x to the sixth power. Right, so x to the sixth power, we can see there is a 2x to the sixth power. Right. There's exactly 2x to the sixth power. And then there is 2b1 x to the seventh power, 2b2 x to the eighth power. So what we then do is we equate. We continue to equate. Right, we continue to actually equate. Coefficients. Coefficients of like powers of x. Okay, now the x to the power 0 would be the following. A0 minus 4 equals 0. And then now we have x to the power 1, which is A1 minus 4B1, 0. We continue to equate. Then we have the quadratic. Like powers of x squared. Four B2 minus 4 equals 0. And then x cubed minus 4b1 equals 0. And then you also have x to the fourth power. Right, so the x to the fourth power is going to give us minus 4b2 equals 0. Okay, we equate everything to 0 because there's 0 on this side. There's 0 on the left of the equation. Now we stop at x to the power 4 because it is R4 of x, and then we ignore the higher powers. We ignore the higher powers. Okay. Right, at this point, I'm doing this because it is one of those questions where you must be rest assured that you pass. You get full marks in this particular question here. This question ordinarily comes at the end. So that is why I'm making sure that I'm doing this first, because it doesn't change drastically. So you therefore have a perfect chance to understand everything. So that in the end, then you get what? You get the following. You have a perfect chance to get exactly the following. So now we pause to reason, but also to examine the findings very cautiously. The question is, can we be able to get the numerical values of the constants at this point? And obviously, I'm sure that you actually are saying, obviously, yes, we can. We can get the constants there. We can get all the values we want. Okay, let us say that. Now, we have said that what you need to do, we equate. We equate the coefficients. And when we do equate the coefficients, we actually have been able to gather some facts. What are the facts? From the previous, yeah, that's fine, can write like that. The x to the naught was associated with a naught minus 4 equals 0. x1 minus 4b1 x2 minus 4b2 x3 right x4 minus 4b2. Let us analyze that together. So we are able to obtain this. And from this here, what is the next step? Is to solve for the unknowns and get the numerical values of the unknowns. And we say, therefore, we have that, like, from this particular equation, it is clear that our A naught is 4. And then when A naught is 4, that is what we're able to get here. From this one, we're able to get that B1 is 0. B1 is 0. From this one, we're able to get that B2 is 0. Dividing by -4. So B1, B2. If B1 is 0, you plug it into this. It means, therefore, that A1 is also 0. B1 is 0. B2 is 0. If B2 is 0, you plug it in here. A2 minus 0 minus 4. So now, okay, this is what we've got. But now you need to recall, what are we then supposed to recall at this point? There are certain things we need to remember, but what should we remember? Recall that. Right, so you need to recall that. You need to recall that R4 of X is actually equal to A naught plus A1X plus A2X squared, all divided by 1 plus B1X, B2X squared. What is A naught? It is 4. A1, A2. A1, you can put 0x. A2 is a 4. X squared, you divide by 1 plus. What is the B1? It is 0x. The B2 is 0, which is 4 plus 4x squared. Okay, yeah, so therefore, it means this is the answer. We can then say our R4 of X is actually the same as 4 plus 4x squared. And this, therefore, becomes the answer we want. So obviously, what have we done? We have found the Pade approximation R4 of X with denominator of degree 2, denominator of degree 2. But if they say denominator of degree 2, you must start with 1. We don't care about what you put as the coefficients of X and that of X squared. And then obviously, because it is of degree, denominator of degree 2, but it's overall degree 4, it must be 2, then this must also be 2, so that 2 plus 2 gives us 4 there. Now, the coefficients here, you can write anything. I mean, you can write x squared plus bx plus c, standard quadratic. And then now in the denominator, you always put a 1, and then you play around with the coefficient of x and that of x squared. But in the end, then you are able to therefore find the Pade approximation R4 of x. And R4 of x is actually here 4 plus 4x squared. And this is the result. This becomes the result. This becomes the result. Next point. Right, the next question is to solve for another economization problem. As part of what we're learning, we must be able to economize. How do we economize? We economize as follows. This is what we do. Right, so we economize as follows. Right, now the first 3 Chebyshev polynomials are T0 is 1, T1 is exactly x, T2 is 2x squared minus 1, T3 of x is 4x cubed minus 3x, T4 of x is 8x to the 4th power minus 8x squared plus 1. Economize the truncated power series. Economize the truncated power series. Okay, now let us continue to check this out. Right, so now the power series given is P of x equals 1 plus 2x minus x cubed plus 3x to the 4th power. Let us economize this and look at how to economize a given power series. Now, this is the story. What you then need to do is to first things first, consider the following scenario. Okay. What you need to do is to consider the following scenario. Consider the fact that we have been given the power series P of x, which is exactly 1 plus 2x minus x cubed plus 3x to the 4th power. So now what you then need to do is to then compare the coefficients. Right, so if you have, for example, this px, which is 1 plus 2x minus x cubed plus 3x to the 4th power. You consider, for instance, the term. So you must reduce the degree, because at this point, what you have here is that the degree, the highest degree of this one is 4. And also the T4 has highest degree 4. So now the question then becomes, what exactly do we do here? You need to perform subtraction. You need to perform exactly subtraction. So if you multiply this one by a certain number, it's going to actually have the same degree, the same coefficient of x to the 4th power. So you can multiply this one by 3 out of 8. T4 of x. Right, so because if you do 3 out of 8, you multiply this, 8x to the 4th power plus 1. Which is 3x to the 4th power plus 3 out of 8. So we multiply through by the 3 out of 8. Why? Because this one, we want to make sure that the coefficient of x to the power 4 is the same. And we achieved that because this is 3x to the 4th power and this is also 3x to the 4th power. So we are getting a step closer to actually economizing then we shall be able to get the economized series. We write the following description that is very important. So we're going to then say subtract. You proceed to then say subtract three out of 8 T4 of x from P of x in order. To remove the highest order term right so as to get the economized series. The economized series. So that you have g of x right. So now we therefore are able to obtain the economized series, and we learn how to, what is to economize a series? To find the economized power series, it's to actually truncate. So economize the truncated power series. And therefore, what we then do to economize, we subtract 3 out of 8 T4 of x from P of x in order to remove the highest order term so as to get the economized series. So you perform algebraic subtraction. So this is therefore P of x. Right, before we deal with the main thing. So it's P of x minus 3 out of 8 T4 of x. Subtract from P of x like so. The answer, what then do we get? We're able to get the following point. Meaning g of x is equal to, what is P of x? Okay, we know it is 1 plus 2x minus x cubed plus 3x to the 4th power. Okay, we're copying this one. Exactly as it is. We minus. So we minus 3x to the 4th power plus 3 out of 8. Which is 1 plus 2x minus x cubed. 3x to the 4th power minus 3x to the 4th power plus 3x squared minus 3 out of 8. Okay, let us check together the algebra. So now, this is what we're getting. The economized series, it's the g function. So you can even write it here so that g of x becomes the same as the following. So now, okay, this is our g of x. So what is it? Let's check together. We're going to add the like terms and things like that. So now we're able to see this guy and this guy cancel out. And we have managed to eliminate the highest order terms. And then we have minus x cubed in descending powers of x plus 3x squared minus 3x cubed plus 3x squared plus 2x. 1 minus 3 out of 8. 5 out of 8. This is the answer. So when they say economize the truncated power series, this is the power series given. You need to economize it, and we have economized it. How to economize is to reduce the highest power to make sure that it is potentially then cost effective. Cost effective. What is the next thing to do now? Is to answer the second part of the question. Give an upper limit for the absolute value of the difference between the original truncated power series and the economized one. For all Chef-by-Chef polynomials. The old Chef-by-Chef. Right, polynomials. What do we have? For all Chef-by-Chef polynomials, which we call T sub I, we have, right, what do we have? We have that the modulus of T sub I is always less or equal to 1 for all. For all x in the closed interval minus 1 to 1. And therefore, okay. Once again, here comes the question, and it says, give an upper limit for the absolute value of the difference between the original truncated power series and the power series. They are the original truncated power series and the economized one. Which means that the original is P of x. And okay. So this is what we did, because now when you look at this equation, we then said from the original power series, you minus 3 out of 8 of T4 of x. Now let us look at this properly. So you perform algebra. Whatever you do, it means that whenever you have g of x minus p of x, it is actually exactly the same as minus 3 out of 8 t of x. Okay, this is what we have. But if you take the absolute value, then, you can play around with this here. But taking the absolute value will actually ensure that you can also, looking at this, you can also, like do it differently. 3 out of 8 t for x, which is px g of x. Okay, we here. So the modulus of p of x minus g of x is actually the same as the modulus of the absolute value of 3 out of 8 t4 of x, like this. But once again, we said that for all Chef-by-Chef polynomials ti, we have that between minus 1 and 1, they are less or equal to 1. The modulus is less or equal to 1. So this one is going to be less or equal to 3 out of 8 because this one is less or equal to 1. And therefore now it remains to use a calculator for the shift by shift polynomials to check the results. So this is then what we do. All right, this is then exactly what we do. We can just confirm this. I know that this is very easy and can be done with so much ease. Okay. So we have the following. So now we're going to take a calculator and say, whenever you have 3 divided by 8, okay, I know this you can done with ease, you rather can do with ease, which is 0.375. 0.375. 0.375. 0.375. 0.375. That is the answer. So obviously the question was in the second Roman figure. Give an upper limit for the absolute value of the difference between the original truncated power series, which is the original truncated power series P of x, and the economized one. This is the original and the economized one. And therefore the difference is that. Therefore the difference is that. Therefore the difference is that. So we continue. So we continue. We continue. Next question. As part of our learning strategies, it is very important to reinforce every concept to learn by not only looking at how this question is asked in one instance, but in several instances. The question then that arises is, what about if they change the numbers? In the concept that we think we so much understand at the moment, but we need to be sure that we can do any question that comes our way. They might not only say the R4, but what about if they say R3 of X? Find a Pade approximation of R3 of X. Okay, if you need to find a Pade approximation of R3 of X, what then do you do here? With numerator, before they gave us, now numerator degree 2 of degree 2 and denominator of degree 1 to the function f of x equals x squared plus the x cubed. Okay, we're mastering this concept there so that we can move on to other concepts. Now, let us ponder on this one. So we know that the Pade approximation is, so now the Pade approximation is going to be exactly what? Be R3 of x. But the numerator is of degree 2, which means A0, A1x, A2x squared, 1 plus B1x. So, in the denominator is of degree 1, but you always put a 1 there. and then you add the B1 x. Because of degree 1, so you stop at the linear the power of x. And then here, this one is a quadratic term in the numerator of degree 2, yeah, to the function this. The Pade approximation, and this gives we can find the difference like we did before. R3 of x minus the f function. What is R3 of x? Is this one? Numerator of degree 2, a naught a1x plus a2x squared divided by 1 plus b1x minus f of x. This one, which is x squared plus x cubed. Which simplifies to okay, so now which is R3 of x minus f of x. Let us simplify this by taking the LCD, etc., which is 1 plus b1x. And then we just add these things up like we did before. Okay, just mastering the concept of Pade approximations, and then we move to other sections. And so at this point, this would mean that we're going to have like a naught, a1x, a2x squared, which is this, minus, then this thing becomes like cross multiplication because it's the same denominator, so it multiplies this. You have x squared, x cubed, 1 plus b1 of x. Okay, so that is what we're able to achieve. R3 minus f of x. Okay, so what then we're able to achieve, because if it becomes a Pade approximation, the understanding is therefore that the numerator will approach 0. So this, therefore, it implies that a naught, a1x, a2, x squared plus x cubed, 1 plus b1 of x is equal to 0. Which is what? a1x, a2x squared. You distribute, you open up the brackets, minus x squared minus b1x cubed. So now, x to the 4th is 0. So now, in the end, so which means there's a1x. Then quadratic is a2 minus 1 x squared. b1 minus 1 x cubed. So we have this. So now, let's continue and be in a position to get the result out of this. So let us take everything into account that we've got. pertaining this problem. 7 marks, this question. So you get this question, you have already passed the exam because it's out of 100 by and large, normally. So if it's out of 100, then you get this mark, then you have sort of passed. Okay, so that will be the C part. So now you then have, we've got A naught, A1x, A2 minus 1, x squared, minus 1, x cubed, to the 4th power equals 0. Equals 0. Equals 0. So what then you're able to get? We do like our usual stuff. We compare coefficients. So by comparing coefficients, we're able to get what we need the most. So we then say to find the 4. Find the 4 unknown values. Unknown values. A naught, A1, A2, and B1. A2 and B1. We must set the coefficients. The coefficients of x to the power 0, x to the power 1, according to this, x to the power 0 for the constant, x to the power 1 for x to the power 2 for x squared, x to the power 3 in the numerator. To 0. This give us the equation. Okay, let us obviously, this gives us the equations. Even here you can say and x cubed. In other words, we must set the coefficients of x to the 0, x to the 1, x squared, and x cubed to 0. So which means, therefore, x to the power 0. Right, so now let us write everything in order. We are ordering these coefficients. So x to the power 0 will deal with the constants, and therefore that would mean a naught is 0. And therefore, x to the power 1, linear. Okay, we'll continue, please. x squared would become the following. The quadratic zero x cubed zero x to the fourth zero. So thus okay, yeah, you actually have sent a message there. Okay, but we are going on. Right, we are going on. So thus, this would therefore mean that, okay, if it kicks you out, please, you try to log in again. Right. Once again, if it kicks you out, try to log in, please. If it kicks you out, try to log in. But this discussion is being recorded, so there's not going to be any interruption. There's going to be a smooth running from beginning to end. There's going to be a smooth running from beginning to end. There's going to be a smooth running from beginning to end. There's going to be a smooth running from beginning to end. Okay, we continue. If it kicks you out, please be glad to just reconnect, please. But once again, because we are recording this discussion, okay, good. Thank you so much. Right, so thus it would therefore mean that A naught is 0 from this. From the second equation, it means that A1 is 0. And then from this one, we can see that A2 is 1. We are able to see okay, yeah, because it's R3, then you stop here. It's R3, then you're going to stop here. You're going to stop at x cubed. Okay. Going to stop at x cubed. Obtaining B1, it's -1. And as a consequence, we're then saying, hence the Pade approximation. Hence, the Pade approximation is, okay, now we know that this Pade approximation is written like this. It's R3 of x, which is A naught, A1, A2, 1 plus B1x. So B1x, A1, B1. So now it's 1 plus B1x. What is A naught? A naught is 0. Take it from here. B1 is a negative 1x. A2 it's a 1 divided by 1 plus the B1. it's minus 1. X. Meaning this R3 of X becomes exactly the following. So what then we're going to get here becomes exactly the following. Yeah? Yes. Okay, this one is A1X, 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 A2. So the numerator is having the A's only. So this one is going to be A0, A1. Which is A1X. What is A1? It's 0. It's 0. So that in the end, divided by 1 minus X. Okay, so we get this. All right, so this becomes exactly the answer, and this becomes the Pade approximation. Hence, the Pade approximation is this one. So in other words, you have learned the Pade approximation. Because it's R3, we're going to stop here at the X cubed. There's no need to proceed to the X to the 4th power because it is R3 of X. After having done that, it's very important to attempt to learn the process of economizing power series. But now sometimes you might need to economize the power series twice. Okay. You might need to economize the power series twice. So if you economize the power series twice, we will take the opportunity to say, we have learned how to economize the power series once, what you call the truncated power series. We can economize it once, but we economized it once before, just in the past couple of minutes. But we might need to economize it like several times. The question then is, how do we then economize it for several times? So yeah, we might need to economize it 2 times, 3 times, 10 times. The prevailing question then becomes, how do we economize it successively? How do we economize the power series successively? We take note of that and we reason that out. We reason that out. And we obtain the following. We obtain the following. Okay. Now, given the power series f of x equals 1 minus x minus 2x cubed minus 4x to the 4th power. So you have been given this power series, but it is standard practice to actually give it with some polynomials. And in this case, our famous polynomials that we know very well are the Chebyshev polynomials. T0x1, T1x, which is x, T2x, T3x, T4x. So economize the power series twice. Economize the power series twice. So we have the following. We need to learn how to economize it twice. Right, so to economize the power series twice, we proceed as follows. We take note of the fact that f of x, this is the solution, 1 minus x, 2x cubed, minus 4x to the fourth power. So you economize it once first, and then you economize it again. So you're going to economize once first. We add. We add or subtract. We add or subtract T4. But not that we add or subtract T4, but like we did before, suitably scaled. Such that the f to the fourth power term disappears. The f to the fourth power term disappears. This is the story, and this is our story. To economize once, we add or subtract T4 suitably scaled, such that the x to the fourth term disappears. So to economize, we need to first get rid of the x to the fourth power, which is the highest one, and then we would have to economize twice, so we would have to also remove the cubic term there. Okay, we continue. So here, we must add. We must add 1/2 of T4. Okay, now this one, because we want to make the coefficient of x to the fourth power suitably the same as this. So we can multiply this one by half. Right. Right. Here we must add half T4. And this half T4, it's half of this. Eight x to the fourth power okay. Okay, we continue, please. So we continue. So now here we must add half T4 of x. which is this, which is 4x to the fourth power, 4x squared plus 1/2. So multiply by that 1/2. And we'll get the economized series. Right, we'll get the economized series. And we'll get the economized series. Right. And we'll get the economized series. And the economized series is going to be F star of X. What would F star of X be? We can see that if you have this one and we have 4x to the fourth power and this, you add them up, the x to the fourth power is going to disappear. Okay, so you have f of x. What is f of x? 1 minus x, 2x cubed, minus 4x to the fourth power. So which means f star of x. Let us look at what we're getting the f star to be. This cancels. These actually cancels exactly, giving us minus 2x cubed. Minus x minus 4x squared minus x. This and that minus x. 1 plus 1/2 is 3 out of 2. So what we then do? Next, economize again. Economize again. So now we need to deal with the x cubed. But we need to deal with the x cubed. So what we're going to do is you need to add 83 suitably scaled. Such that the x cubed term disappears. So we continue. disappears. Right. Okay. So now we need to economize again because we economized the first and then we need to economize again. So we can economize like many times, a finite number of times at least. So to economize again, what we do, we add T3 suitably scaled such that the x cubed term disappears. We must add okay. Okay, now because we economized and got f star of x, and this f star of x became minus 2x cubed minus 4x squared minus x plus 3 out of 2. So if you look at the x cubed, this one, we want to make the coefficient of x cubed the same. So we must add 1/2 of T3 of x. What is T3? So you have 2x cubed, 3 out of 2x. This is what we're getting. And because T3 is this one, you take half of it. We continue right now and we're able to get the following. Okay. And we'll get F double star of x, which is the second economized series. And then now we remember that we've got the first economized series, which is F star of x. Plus 1/2 T3 of x, which is minus minus 2x cubed minus 4x squared minus x plus 3 over 2. What is half T3 of x? Is this plus 3 over 2x? And what is this? Okay, obviously, by looking at this carefully, we are able to make certain observations like the cubic terms disappear. Minus 4x squared. Right, so we have minus 4x squared. Right, so we have minus 4x squared. And then we're able to obtain the following. Minus 4x squared. Now we have to deal with p over 2x minus x, 2 out of 2, which is x out of 2. Right? Let's check this out. Let us check this out. So this, therefore, is going to be exactly x out of 2. Which is plus 3 out of 2. So this becomes, therefore, the answer. At this point, we have to economize the power series twice. And this is what we have done. This is what we have done. This is what we have done. Okay. And then now we got F double star, which is exactly this. So it's minus 4x squared plus x over 2 and a 3 out of 2. So we've economized this power series problem twice. But now we need to answer the next question. The function e to the power x is to be approximated by a 4/5 order polynomial over the interval from minus 1 to 1. Why is the chef-by-chef series a better choice than a Taylor or Maclaurin expansion? The function e to the power x is to be approximated by a 5th order polynomial over the interval minus 1 to 1. Why is the chef-by-chef series a better choice than a Taylor or Maclaurin expansion? So we continue. We continue. Okay. We read the question again for the 4 marks. The exponential function, the function e to the power x, is to be approximated by a 5th order polynomial over the interval from minus 1 to 1. Why is a chef-by-chef series a better choice than a Taylor or Maclaurin expansion? Let us analyze this together. And the reason for this would be the following. Right, we note that the maximum error over the whole interval, is smaller the maximum error over the whole interval is smaller, the Taylor series has zero error at x equal to 0. But the error can be quite large. Can be quite large at x equal to plus or minus 1. So now we're then effectively, to answer this question for the 4 marks, we are first saying the maximum error over the whole interval is smaller. The Taylor series has zero error at x equal to 0, but the error can be quite large at x equal to plus or minus 1. So we continue. We continue. Right. Okay. Okay. Right. Okay, we continue, please. We continue. So, but that will be the answer. That will be the answer. So that will be the answer. So the maximum error over the whole interval is small. The Taylor series had zero error at x equal to 0, but the error can be quite large at the extremes, at plus or minus 1. So in other words, the function e to the power x is to be approximated by a 5th order polynomial over the interval. Why is the chef-by-chef series a better choice? Now we're saying, why is the chef-by-chef series a better choice than a Taylor or Maclaurin expansion? Because the maximum error over the whole interval is smaller, but also the Taylor series has zero error at 0, but the error can be quite large at plus or minus 1. And hence, a chef-by-chef series is certainly a better choice than what we call a Taylor or Maclaurin expansion. We continue to check this out. Right. Okay. Next. Next. Right. There are a couple of things we need to study. A couple of things we need to study here. And I want us to learn how to solve a wide range of problems. In this case here, I want us to learn how to solve a wide range of problems in this case here. And we continue to practice even much more. And I want us to spend time on this particular type of problem. Okay, I want us to spend some time on a wide range of problems. One of the most famous methods is the notion of this one, the Adams-Moulton method. Adams-Moulton method. Right, so in the case of the Adams-Moulton methods, let's practice with the Adams-Moulton method, which I'll learn a couple of other methods. But now we are doing what we call the predictor corrector formulas of the Adams-Moulton method. So what are the predictor corrector formulas? And you are told that. So we need to just learn these and make sure we know them. Normally they are given in the exam, but it will help to actually, master them and know them off by heart. Right. So the predictor corrector. The predictor corrector formulas of the Adams-Moulton method are the following. Yn plus 1 is Yn plus h out of 24, open bracket 55, f sub n minus 59 subscript n minus 1 plus 37, f subscript n minus 2 minus 9, f subscript n minus 3, plus 251 divided by 720 h to the 5 y to the 5th power, evaluated at xi1. Right, so that is the predictor, and then the corrector. The corrector is Yn plus 1. So in other words, this one here is the predictor. Okay, this is the predictor, and then we have also the corrector. This one here is the predictor. And this one becomes the corrector. Right, so we continue to analyze this very carefully. Let us zoom in to these methods here before we even solve the problems on the Adams-Moulton method. The predictor formula, what is the predictor formula? You need to memorize it. You need to learn it. You need to understand it before you even apply the methods. Predictor is Yn plus 1 equals Yn plus h out of 24, 55, f subscript n minus 59, f subscript n minus 1 plus 37, f subscript n minus 2 minus 9, f subscript n minus 3 plus 251 over 720 h to the power 5, the fifth time the fifth derivative evaluated, the fifth derivative of y evaluated at xi1. That is the predictor. The corrector is Yn plus 1, which is Yn plus h out of 24, 9fn plus 1 plus 19fn minus 5nn minus 1 plus fn minus 2 minus 19 divided by 720. H to the power 5, y fifth derivative of y evaluated at xi2. So these are the predictor and corrector. Both of them are Yn plus 1, Yn plus 1. Both of them have Yn. Both of them have h out of 24, h out of 24. But the difference becomes in the subsequent terms. Right, in the subsequent terms. Okay, apply the following. You need to apply the Adams-Moulton method to calculate the approximate value of the function. Apply the Adams-Moulton method to calculate the approximate value of y at 0.8 and also y evaluated at 1.0 from the differential equation. From the differential equation, you need to approximate the values of this y evaluated at 0.8, y evaluated at 1.0 from the differential equation. And the starting values are the following. T evaluated at 0.0, at 0.0, yt evaluated at 0.95, t at 0.2, 0.68, t at 0.4, 0.55, t at 0.6, 0.30. Use 3 decimal digits with rounding at each step. Okay, use 3 decimal digits with rounding at each step. Okay, let us learn the methods here and appreciate the Adams-Moulton, a very examinable method stage. So to answer this question, we begin as follows. Right, so we note that we say C, which is y primed, it's t plus y. But this, it's f evaluated at t and y. Okay, continue. The given starting values. The given starting values are n equals 1, n equals 2, n equals 3, n equals 4. And then you have the values of t. T1 is 0.0. And then there's T2, 0.2. T3, 0.4. T4, 0.6. Y1, we have the following. Okay, so okay, now let's deal with the y's. Y1 is 0.95. Y2, 0.68. Y3, 0.55. Y4, 0.30. And then now we're gonna determine the F's. F3. Okay, now there's F1, F2, F3, and the F's come from the fact that the differential equation is now called a function of t and y, multi-variable function of t and y. And we're able to determine this function like f1. So f1 becomes the sum of t and y. So here you're going to add t and y. But this is just 0 plus 0.95. So you're going to only get 0.95. Then here you're going to add this and that. But 0.2 plus 0.68 would give us 0.88 because it's t plus y. 0.4 plus 0.55 would give us 0.95. 0.6 with 0.3 would give us 0.9. Okay, so we've completed a table of the F's, the Y's, the T's, and the N's. Let us first calculate the predictor. The predictor is let's check, take a look here. So the predictor is the first one. Yn plus 1 is Yn plus h out of 24, 55, n minus 59, fn minus 1 plus 37, fn minus 2 minus 9, fn minus 3 plus 251 out of 720. So now, so you have Yn plus 1. So now, h out of 24. Fn minus 59, Fn minus 1, 37, Fn minus 2, 9, Fn minus 3, so now, plus this. And now, if you're going to do, so we're dealing with the predictor. So the predictor now, because you can see that this y is there, you have y1, y2, y3, y4, then we must do y5. Y5 then is going to be y4. H out of 24. Which is 4. And then we are putting 4 in the place of n. 4 in the place of n. This one is going to be 3. 4 minus 1 is 3. 4 minus 1 is 3, and then 4 minus 2, it's 2. 4 minus 3, it's a 1. Okay, now what is y4? 0.3. Y4 is 0.30. So now, obviously, the fact that this is 0.0, 0.2, 0.4, 0.6, the difference here is 0.2, 0.2, which means that H is 0.2. Which means that H is 0.2. F4. F4 is 0.9. F3, 0.95. F3 is 0.95. And then there is 37. F2, 0.88. F2, 0.88. F1, 0.95. Okay. Now this is the case, and then you're getting Y5. Let us use a calculator to get the answer here. Okay, let's use a calculator to get the answer. So now here we're going to use the taskbar. Which is 0.30. Not 0.2 divided by 24. 55 times. Minus 59. Not 0.95. 37 times 0.88 minus 9 times 0.95. Close bracket. Not 0.4455. Not 0.4455. So the F5, according to this, because this is FXY, so the F5, according to this, it's going to be T5 plus Y5. What is T5? We saw that this is T1, T2, T3, T4, T5, you add 0.2 because it's 0.2, 0.2. You add 0.2, you get this. 0.2, you get 0.4. You add 0.2, you get 0.6. You add 0.2, you get that. So now we have Y5. Right. Right. Okay, T5 is 0.8. That's what. T5 is 0.8 here. Check. So you're going to do 0.8 plus 0.4455. 1.2455. 1.2455. 1 point. Right, so we have exactly 1.2455, which is F5. So now, now we have found the predictor. We found the predictor, and then you find the corrector. And the corrector is right. So come to the corrector. Remember that the corrector is yn plus 1, which is yn plus h over 24. Yn plus 1, the corrector. Yn plus 1 is yn plus h over 24. Open bracket. 9 fn plus 1 plus 19 fn minus 5 fn minus 1 plus fn minus 2, close bracket, minus 19 over 720 h to the 5, the fifth order derivative of at xy of y at xi2. This is the corrector. But we want to obtain y5 of this, so we proceed as follows. And the corrector is, so we're going to do the corrector. Yn plus 1 plus fn plus 1 and then plus $20. So right. Okay, so continue. Okay, continue. Okay. Let us get the answer. Let us get the answer. Okay, let's get to this point. Okay, now we are getting the corrector. But you see, the way we're getting the corrector now, then we need to get y5. When n is 4. And then when n is 4, when n is 4, when n is 4, when n is 4, which means y5. So what is y4? y1, y2, y3, y4. y4 is 0.3. H is the difference here. H is 0.2. What is F5? Check here. F5 is this one, 1.2455 from the predictor. 1.2455. What is F4? F4, you already know, we said it is 0.9, but yeah, we got it here. F4 from the table we drew is 0.9. That is F4. 0.9 minus 5. Then we have F3. F3, 0.95. 0.95. F2. F2, 0.88. 0.88. 0.88. And then now we just use our calculator to get the answer here. So the corrector is that one, and then now we're gonna do the following. Using a calculator. So what we have here is that we have 0.3 plus 0.2 divided by 24. 9 times 1.2455 plus 19 times 0.9 minus 5 times 0.95 plus 0.88. Okay, let's see what we're getting here. Let us do this again. Let's see. Ah, okay, there's a small typo here. The decimal point is missing. 0.3 plus 0.2, 24, 9 times 1.24, 55 plus 19 times 0.9 minus 5 times 0.95 plus 0.88. Okay, let's check this one. 0.5036625. So you can round it off to 0.5037. And then now you need to get F5, and F5 is, according to this is FTY. So F5 is T5 and Y5. 0.8. 0.5037. So that in the end, .8 plus 0.5037. Okay, then we're getting F5 is 1.3037. 1.3037. 1.3037. That is our F5. Next. We actually now found the predictor and the corrector. And so we're going to therefore continue, and we're going to compute it the next step. Next, we then say, for example, at t equals 1.0, the predictor is okay. You'd remember that you already know the predictor. It is yn plus 1, which is yn plus h over 24, 55. Fn minus 59. Fn minus 1 plus 37. Fn minus 2 minus 9. Fn minus 3 plus 251 divided by 720 H5 XI1. And then at this point, this one is the predictor. But you're going to get Y6. Y6 means that N is 5. Y5, H out of 24. F5 minus 59, 4. 3. N is 5. 2. Because it's 5 minus 3, which is 2. And then you leave out the other term. Y5. You have already got Y5, which is 0.5037. H is 0.2 divided by 24. 55, then you have F5. F5 is 1.3037. F5 is 1.3037. 1.3037. F4. What time is your meeting? What time is your meeting? F4. F4 is 0.9. F4 is 0.9. F3. F3 is 0.95. F3 is 0.95. 0.95. F2. F2 is 0.88. So now we have y6. So now 0.5037 plus 0.2 24 55 times 1.3037 minus 59 times 0.9 plus 37 0.95 minus 9 times 0.88. We close the brackets. 0.8856. .8856. F6 according to this, because this is f of ty, t5, y5. What is t5? t1, t2, t3, t4, t5. t5 is 0.8.
Sorry to interrupt.
Yes, please.
I just want to know, why are we not adding the 251 over 720 when we are working out y6?
It's the order term. We don't add the order terms. Okay, yeah,
Oh, okay.
that's the point. Because it's an order term, that one, it is h to the 5. Normally we then say the order has to do with the dominant terms, or the terms, or the term of the highest degree. But I'm going to discuss the order terms at some point, but we never add the order terms. We don't add them up.
Oh, all right.
Just
Okay.
for operational purposes, they give the equation some character. They characterize the equation, then, so they don't have any numerical significance. Quite. Okay.
All right.
So good. So that now you have T5 and then the H and the Y5. So what is T5? T5 is 0.8, and then Y5. We got our Y5, and we got our Y5 to be exactly what we got, which is 0.50. Y5 is 0.5037. So it's 0.5037. And then you add these things. Let us add this up with a calculator just to make sure we cross-check our answer. Right, so now what we're then getting is we have this one, 0.8 plus 0.5037, which is 1.3037. Right, so you're getting exactly 1.3037. So if you have your okay, there's something I need to add here. What I'm saying here is that the F6 is T6Y6. That's what I'm saying. So it is T6. And then obviously if this is T5, then T6 is going to be 1.0, which is what we want. So now you're then going to say the T6, which is 1.0 plus the Y6, right? So obviously at this point, we have obtained the Y6, which is 0.8856, and the sum would be 1.8856. Okay, so this has given us F6. We continue right now to look at the next thing. And what then we are then saying here is the following. And the corrector. So now we've found the predictor. The predictor def is F6, and then we find the corrector. So, but at t equals 1.0, we found the predictor, and then let us find the corrector also. So at t equals 1.0, the corrector is, okay, you would remember the corrector formula, you already know it because we saw it in the question. The corrector is in the Adams-Moulton. There are different methods we're going to discuss, but Adams-Moulton is one of those techniques you need to learn. And then we shall discuss the other subsequent techniques after the Adams-Moulton. You have a yn plus 1. Yn plus h out of 24. 9 fn plus 1 plus 19 fn minus 5 fn minus 1 plus fn minus 2 minus the order h5 y. Order 5, and therefore this is xi2. So now you then have y6. So now corrector y6 would be n is 5. So here you have y5. H out of 24, 9 f6, 19 f5, 5f, if 5 minus 1 is a 4, 3. Y6. What is Y5? Y5 is 0.5037. That is Y5. 0.5037. H is the difference between the t values, 0.2, the 0.2 difference, 0.2 difference. In terms of saying the subsequent one minus the previous, like 0.6 minus 0.4 giving us 0.2, 0.4 minus 0.2 giving us 0.2. At this point, we have exactly 0.2. Divide everything by 24. Why 24? Because that is the formula for the corrector in the Adams-Moulton method. 9 multiplied by f6. We have already got f6. What did you get f6 to be? We got it to be 1.8856. 1.8856, close bracket. 19 f5. F5. $1.37. 1.3037. That is F5. F4. F4. Right, F4 is 0.9. F4 is exactly 0.9. .9, and then we have F3. F3 is 0.95. F3 is 0.95. So that you have Y6. 0.5037. Not 0.2 divided by 24. 9 times. 8856. 19 times. 1.3037 minus 5 times 0.9, 0.95, okay, let's check this one. 0.822, 0.822. Right, so at this point, it therefore allows us to then say the y of this is approximately 0.822. Why at 0.8? Because we're supposed to find the approximate value of 0.8 and 1.0. The 1.0 is 0.822. And the 0.8 is what we got the corrector is actually it gave us this one, which is 0.5037, 0.5037. So this one is 0.5037. 0.5037. 0.5037. That is what we've got. Right, so apply the Adams-Moulton method to calculate the approximate value of y evaluated at 0.8 and at 1.0 from the differential equation. This is what we're getting. So the y at 1.0, the corrector is this one, 0.822. And obviously, the corrector here gives us exactly that. So in the end, then the actual accurate values would be the approximate values, obviously, we to approximate is 0.8 for the 1.0 corrector. At 1.0, the corrector is 0.822. And then at 0.8, it is 0.5037. And therefore, for today, we are done. We have just discussed this Adams-Moulton. We've solved this problem in some detail. Please give it some thought and see if you understand or not. We shall meet then again in our next meeting. And we shall send you the recording in the next couple of minutes. Right. We shall send you in the next couple of what? We shall send you this recording in the next couple of minutes so that you can be in a position to interpret this very, very well. Okay, obviously, you have a fair chance to, you'll be, we record these here. So,
Okay.
why do we record? Because there's no way the system can kick us out, for example, because we are on the system. I mean, the Zoom can't kick us out, but it can potentially kick you out because you are joining, but we are hosting you. You can, normally it works like that. That's how the Zoom works. Okay, but Aman, thank you for joining us. We are sending you the recording in the next couple of minutes. Our meetings are on Tuesdays, Thursdays, Friday, Saturday. So
Yes.
it's Tuesday today, and then the next one is on Friday. It's on Thursday. It's on Thursday. Right. So we thank you for joining us. We shall send you the recording. You shall participate and just make sure you understand the two methods we discussed today. What are the two methods? We discussed the Pade approximation. We discussed the method of economizing a power series. We economized a power series once, but we also went on to economize a power series twice. We went on to look at the Adams-Moulton method in relation to finding approximate values of a given function, of a given differential equation by means of the predictor and corrector formulae. Right, we must thank you for joining. I know that we have gone beyond the time, but thank you for joining us. Until Thursday, we shall send the recording and we chat on WhatsApp. But take care and goodbye.
Thank you. Bye.
Thanks a lot. Goodbye.